So the next talk is making progress in property-directed reachability, and is going to be presented by Tobias Seufert.
Yeah, yeah, Seufert.
Please go ahead.
Okay, so you can hear me properly, and also can see the slides, hopefully. Okay. All right then. Yeah, thank you very much for the introduction. And today we will discuss an algorithm which we named Progress in the context of formal safety verification with property-directed reachability, also known as IC3. And of course, this is joint work with my advisor, Christoph, and our colleagues from OneSpin, Arun, Sven, and Tobias. Okay. Yeah, so just a quick definition of formal safety verification. So we have given some transition system M and a property P, and we would like to prove whether P holds in all reachable states of this transition system. And we can also reformulate this as a reachability problem, which asks whether it's possible to eventually reach a state which violates this property P. And we call such an error path a counterexample here. And well, formal safety verification, of course, suffers from state space explosion. And there are many countermeasures, of course, but one popular one would be abstraction, which is just an over-approximation of the behavior of the transition system with the idea of simplifying it by that. And one could achieve an abstraction by, for instance, abstracting away state variables and just considering them as user-controlled inputs. And yeah, by that, we would, in the abstract transition system, introduce transitions which are not present in the concrete transition system. And as a result, we could find spurious counterexamples in our abstract transition system. Proofs, however, are always valid. And usually one would combine these abstraction techniques with a refinement technique, and very popular here would be SIGA, which is short for counterexample guided abstraction refinement, which just uses these counterexamples to or use information from these counterexamples, these spurious ones, to refine the abstraction in some kind of a loop. And of course, in contrast to abstraction, there's also restriction, which it's kind of the opposite, which builds an under-approximation in order to simplify a transition system. And that could be achieved by, for instance, considering state variables or user inputs as just constants or anything else really. And so restricting them to specific valuations. And by that, in contrast to abstraction, we would remove transitions from the original transition system. And as a result, we would find valid counterexamples, but we could run into spurious proofs, of course. And well, these restrictions, they are a commonly used technique. For instance, in interactive bug hunting, where you would restrict parts of your design, where you use restrictions to maybe deactivate parts of your design which you consider irrelevant for disproving some property. And maybe a simple example could be an ALU where you only want to find bugs in your multiplier unit, then maybe you could restrict some control signal of the ALU to just multiply. And where we were searching for fully automatic approaches here actually, which do not require any prior knowledge or which require only limited knowledge to the design beforehand, like something like Seeker, but we couldn't find anything, so we thought that we had to introduce progress here, which is short for proof-guided restriction skipping. And we thought of this as the duel of Seekers. So instead of refining an abstraction by using spurious counterexamples, we want to coarsen or relax a restriction guided by a spurious proof. And to give you a quick overview how these two relate here, I have an illustration. So on the left-hand side, we have Seeker, and general flow would be that Seeker starts with an abstraction, and if it finds a proof, then we can report safety, of course, because proofs are valid under abstractions. If we find a counterexample, however, we have to check whether or not it's spurious. And if it is spurious, we refine the abstraction and start over. And with progress, it is similar. We start with a restriction, and now a counterexample. So if we find a counterexample, this will be valid, and we can report unsafe. If we find a proof, though, in the case of progress, the proof may be spurious, and if it is, then we can use it to relax our restriction and start over. As a result, we are left with a fully automated and complete algorithm here for model checking under arbitrary restrictions, really. So one could fix variables to constants or introduce any arbitrary constraints over state or input variables and so on. And also, we think that this can be applied to any model checking algorithm, actually. But we focused on PDR in our work. And let me just quickly justify why. Because in hardware verification, we really consider, and this is a wide consent, that PDR is the most efficient standalone verification engine there is. And also, PDR is able to find deep counterexamples, and this is what people usually would want to find when they impose restrictions on a system. And yeah, I will just quickly give you an idea of how PDR works here. So let me start with PDR without any restrictions whatsoever. So I talked about safety verification, and that is what PDR tries to achieve, of course. And when we take a look at this illustration here, you want to outrule that there are counterexamples which start in the initial states here and find their way to some bad state, which I have depicted with this not P here. And so PDR wants to find a strengthening of the property, which includes the initial states, which is safe in a way that there are no bad states included, and which is closed under the transition relation. And that is what we call here a safe inductive invariant. And well, now the question remains how PDR does that. So it maintains these time frames Fi here, which are actually over approximations of the reachable states within I steps. And the ultimate goal would be to find one of these time frames which can act as a safe inductive invariant. And yeah, still I haven't told how PDR creates these. And it really does it by searching for one step. Sorry, I will illustrate this on the example of the next time frame, which would be due here in this example, which is just fk. And so PDR would try to find one-step predecessors of the unsafe states or bad states, which are called proof obligations, because we have to prove that they are unreachable within k steps, of course, because otherwise we would have a counterexample here. And PDR outrules this reachability by just checking reachability from, or one-step reachability from the previous over-approximation. Because if we can find a transition from an over-approximation for reachable states within k-1 steps, then we have also proven that state is unreachable within k steps. And PDR also generalizes the single state to a whole set of unreachable states, and in the end we have such a cube C1 here with which we can strengthen the property by just adding its or conjoining its corresponding clause, which is not C1. And yeah, once PDR has resolved all of these proof obligations, where we are given such a set of clauses, or also called blocked cubes, because they are removed from state space. And now the question remains whether this is closed on a transition relation. And if it is not, then we have to continue with a new frame and so on. But if it is, then we are left with such a safe inductive invariant here. So this set of clauses would act as a proof of safety here. Okay, so enough for standard PDR. Now what happens if we impose restrictions on PDR? Then we could end up with something like I've illustrated here. So it could be that we block a cube prematurely under restrictions, because we could have a scenario like this here with a restriction which removes just these two red transitions here and concludes that C1 is unreachable, but which it really is, because in the original transition system there are these two red transitions. So when we can find such spuriously blocked cubes, then of course, since our proof really consists of these blocked cubes, then it is clear that we can also find spurious proofs if we have restrictions in PDR. But what about these proof obligations? Well, I said restrictions, they remove transitions from the original transition system. And then, of course, we may miss proof obligations which are present. But if we find proof obligations which are, in a way, candidate counterexamples, then these are valid, of course. And therefore, also our counterexamples that we find on the restrictions are valid. Okay. Well, so now that we have the idea of progress and the idea of restrictions in PDR, we can like merge these to an algorithm which runs PDR under restrictions to the transition relation. And then we have two possible outcomes, basically. So the first case would be that we find a counterexample, and then we can conclude that our design is unsafe because counterexamples are valid. The second case, though, is that we find any proof, and of course that proof can or may be spurious, and that is why we have to examine it further. So to give you an idea here, what can happen is we could find such a safe inductive invariant, and now the question is this really a proof, or are there any transitions in the original transition system that we missed under restrictions which invalidate our proof? And it's really relatively easy to check this. So we just query a set solver with this formula here, and we use an unrestricted transition relation, of course. So if we ask the set solver whether this is satisfiable or unsatisfiable, then we have, of course, two cases, and the first one would be that it's unsatisfiable, and then we are happy, of course, because we have proven that this is also a proof of safety under the original transition system. And there's also the other case that this is satisfiable, which means that we found a spurious proof here. And now we would like to proceed. We don't want to just conclude, oh, yeah, it's a spurious proof and we are done. But we'd like to proceed and want to find the restrictions which are actually responsible for us running into this spurious proof. And for that, we just add the restrictions that we had in our run to the set solver, and we query it again with the same formula. And now we know that this will be unsatisfiable. It's clear to see. I mean, we use just the same restrictions as beforehand, only just as assumptions here. And the interesting thing, though, is that the unsatisfiable core now reveals a subset of these restrictions, which is responsible for finding the spurious proof here. And what we do now is we retract these restrictions and we restart and just run PDR again with this new weaker restriction. And we can even, when we use PDR, we can even reuse information from the previous run. So for proof applications, that's obvious, of course, because they are valid anyway. And we can also, under some circumstances, reuse block cubes. But we have a more detailed discussion on this in the paper. This would be out of scope here. And okay, so now to be more practical, I'd like to present our implementation here. And this is based on the bit level well-known IC3 reference implementation from the original author, Arun Bradley. And what it does is it really combines this progress PDR approach with a standard PDR engine to get the best of both worlds. And we really start progress PDR and impose restrictions once PDR gets stuck, which means that it's not able to advance anymore with new time frames. And well, this is really a proof of concept implementation here. So what we do is we start with really simple restrictions, just setting inputs and state variables to constant zeros. And what it is able to do, it can really process any Eiger design without any tinkering whatsoever, which are also used in the hardware model checking competition, which is exactly where we get our benchmarks from. And as a reference, in the results that I will be presenting in the next slide, we've also compared us to state-of-the-art implementations of PDR and bounded model checking. And we also compared us to a PDR implementation with kind of influence reduction pre-processing. And that is because we feared that our restrictions could somehow implicitly remove or deactivate the part of the design which is syntactically irrelevant to disprove our property. And well, as a timeout, we set 1 hour and 7 gigabytes as memout. And first of all, our overall results, and by overall I mean on safe benchmarks as well as unsafe benchmarks with counterexamples present, And as you can see, our implementation is even stronger than the PDR competition on both worlds, like safe and unsafe benchmarks. But more significantly, or more interestingly, when we consider only unsafe benchmarks with counterexamples present, then this gap even widens. So our progress PDR here in green is significantly stronger than any other PBR implementation that we've compared it against. VMC, however, meets our result. This does not really come as a surprise, though, because VMC is widely considered stronger for bug hunting than PDR. And you can see that that the VMC implementations are stronger than the standard PDR here on counterexamples. When we consider deep counterexamples, however, and this is like somehow the key insight here of our paper, then we can see that our implementation really excels. And even standard PDR implementations are better than bounded model checking here. But our progress PDR can even like double the amount of found deep counterexamples than bounded model checking. And of course, I have to tell you what we understand by deep. We consider counterexamples as deep when their length is greater or equal to 30. So, well, we had some other observations, of course, when we ran our experiments. So, as expected, restrictions make PDR advance more quickly and, of course, more deeply into the design. And we also saw that progress PDR really excels with especially deep counterexamples, but it's also good for safety proof, which came a bit as a surprise. So it like meets the result of standard PDR with respect to safety proofs, and there are even some unique solves here. And yeah, well, some other stats. So when we solved something under restriction, on average, we had still half of our initially restricted variables under restriction. And then on average, we required like 5.65 restarts of our progress algorithm due to spurious proofs. And what's also interesting is that the problems which are solved by VMC and progress PDR are complementary. So we observed that VMC is rather strong with short counterexamples, and of course progress PDR is stronger with deep ones. And this is also kind of expected because the deeper the counterexample, the more or the heavier the load of the set solver with VMC, because you have like huge unrollings here. And yeah, well, to conclude my talk now, so we have seen a really fully automated framework for model checking with restrictions, and we have seen that by imposing restrictions and by using progress, we can help PDR's capabilities of finding counterexamples, and of course, especially deep ones. And even our naive, really brute force approach seems to be effective even without any user knowledge of these competition designs. So maybe for future work, it's left to think of more elaborate restrictions, of course, and maybe have a closer look into how or what happens in these designs when we verify them with our progress PDR. Okay, so yeah, thank you very much for your attention, everyone. Yeah.
Thank you for the talk. Are there any questions in the room? I assume someone will tell me if they are.
I don't see any questions right now.
Okay, I have a question. This might be a silly question. I don't know. So you've talked about progress PDR, and you said this is good for deep counterexamples, and then you said, oh, but BMC is actually quite good for counterexamples. Could you have progress BMC? Is there a reason? Could you adapt your progress technique to combine it with bounded model checking, and then be good at really, really deep counterexamples?
Yeah. Actually, everything here comes from VMC, because at one spin they were experimenting with bounded model checking under restrictions. And I think this is what you usually would do. But the problem with bounded model checking, of course, is that it's incomplete. You wouldn't find the proof here, so you would require something like Craig interpolation or K induction to have your to find the proof, which you could analyze and then relax your restrictions again. So, but yeah, of course, if you have a complete engine for safety verification, then you could also adapt the progress approach to that implementation. Yeah.
Okay, thank you. Are there other questions? I have one more as well. So you mentioned that this sort of brute force approach, where you're not combining you don't have any knowledge about the underlying design, is still effective. Have you thought about how you could combine this knowledge, like any underlying knowledge? Like, if I had it as a user, is there a way you could incorporate that into your technique?
Not in a fully automated way, I suppose. But if you have one specific design and maybe it's some protocol implementation, something like that, and you know which lines are data lines and which lines are control logic, then you want to disprove a property which only talks about control, then you could maybe come up with restrictions to data lines, something like that. So I can only think of any specific approaches, like if you have knowledge of a specific design. But maybe you could also have this created in some automated way, of course.
Okay. Okay, yeah, thank you. That answers my questions. If there aren't any other questions from the room, thank you very much to all the speakers.